Okay, I think you see my desktop, and we continue the last shell session about load flow with Gauss Seidel. In the last session, we talk about the group of buses. The buses divided to three group: PQ buses, PQ buses, or load buses, in which in this bus P and Q is determined and specified. When you have a PQ bus, you can set P and Q as determined amount, and you can suppose P, D, and Q demand is determined, and no generation is here, only demand or load. Specified, specified, and which parameters you have to find is Vi, the magnitude of voltage of bus I, and its angle. These two parameters is unknown. Another part, another group of buses is PV bus. PV bus is a specified buses which have generator or generation. For example, this bus is PV bus. Which parameters is specified? P and magnitude of voltage. Pi and magnitude of voltage specified, and which one is unknown? The angle of voltage and reactive power. The group number 3 is slack buses. A slack bus is a generation bus which you can suppose the magnitude of voltage and its angle fixed or specified. For example, a slack bus has 1 per unit with angle of 0. Another example, the slack bus is 1.2 per unit with angle of 0 degree. The magnitude of voltage of a slack bus and its angle is specified. Which one is not specified? A slack bus, a slack bus uh, act as serving to compensate amount of power which can be not more than the bigger one, and its size is not important, but the ability of a slack bus to fill the a small gap to fix the frequency and help to improve your grid stability. In a slack bus, which parameters is unknown? P and Q is unknown. Okay, these subjects we discussed before in last session, and in this session we try to talk about the limitation of generation, the generation power generation limit. One of the limitation of power in a power plant or generator is this equation. In each power plant we have PGI minimum and PGI maximum, and your generation must be between maximum and minimum. In other words, it is impossible to generate zero power. For example, in a power plant which is located in bus number 1, generation 1, and P generation 1 and Q generation 1, and other part of network is here. In this network, for example, the nominal active power of generation is, for example, 2500 megawatts. This is a nominal. P generation in nominal mode, nominal or full load. P generation in full load is 2500 megawatts. But the maximum the maximum of generation PG1 maximum can be, for example, 2600 megawatt, and P generation 1 minimum 50 megawatt. It is impossible to generate less than 50 megawatt. Why? Why we cannot generate less than 50 megawatt, for example? It's because of mechanical construction of generator imposed us to set a minimum generation. For example, for this power plant, the minimum amount of power, active power, is 50 megawatt. And the maximum generation is obviously in each power plant we have an amount of maximum generation. Another another important equation or expression is about the limit on reactive power generation. In each power plant, we have your reactive power generation of bus number I is limited to its maximum and minimum. Like active power, reactive power also have limitation. The reactive power composed from excitation. Let's to review synchronous generation. I prefer to review the synchronous generation for you, and okay. In asynchronous, in synchronous generation or generator, we have a fixed part as a stator and rotating part called rotor. And in this clip, you can see the rotor which is the wiring process is done, and the wiring process and the wiring of the rotors make make and make an excitation circuit. The excitation of a rotor finally makes reactive power. For example, here, this is a synchronous generator and its rotating part, and this called uh, excitation circuit. In 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 synchronous generator, the fixed part is a stator, and there are some windings here to make three phases: phase A, B, and C. And this called terminal. Can I ask you to shut down your microphone? Everyone, please. Mr. Ahmed Talib. Salam alaikum. Please turn off your microphone. Thank you. The stator windings make generation, and we extract the energy from these three phases windings as phase number A, B, and C. The rotating part is rotor, and its winding is connected to a DC voltage. And the role of the rotor is generating flux. Generating flux. And after connecting to DC voltage, this part and the rotor is generate flux. Phi. And this phi passes through the stator windings and induce voltage over the stator windings. This phi is a rotating phi. Rotating phi. Because of the rotating the windings of rotor with the speed of omega m. The rotor turn around with the speed of omega m, and in result the flux, generating flux, rotate with the speed of omega m, and this speed and this rotation flux make an induced voltage over the wiring on a stator. This current is called IF. IF is current of rotor windings, and it is called as excitation current. Excitation current. Excitation current. Or field current. Field current. The field current is a crucial rule to generation of reactive power. So, flux, IF can determine reactive power. IF is limited between minimum and maximum and minimum. And so, in result, we have Q generation from bus I is limited to maximum part and minimum part. So, in synchronous generator or power plant, we have two main limitations about active power and reactive power. Okay, another important part is about this main equation. What is the equation? This equation tells us about the equality between generation and consumption in active power or reactive power. Generation, consumption. These two expressions must have equal to each other. For example, we have in power system, for example, 10 power plant, and the sum of active power of these 10 power plant is sigma Pg. Sigma Pg in the left hand. In the right hand, we can write consumption or loads. PD, sigma PD means the sum of loads, and another loads is losses. Sigma losses means loss. loss divided to two main parts. One part is transmission loss or ohmic loss or Ri2. Another loss is using electricity without any charge. In other words, is electricity theft. For example, in distribution network, you get power in behind of your counter, behind your counter, without any calculation of which power you use. This also called losses. A reactive equation and balance in power plant balance. Reactive is written like active power. The sum of all reactive power in generation must be equal to sum of all load demand of reactive power and its losses divided to transmission losses and other usage of reactive power without any counting. Do you have any problem? Question? The generator the generator have to supply both them, even loads or losses. The generator should be generate even losses. But in reactive power, I think it is important to write only only generator, only power plants can generate active power or P. Only power plants can generate active power, but power plant and capacitors, power plants and capacitors can generate reactive power or Q. And capacitor help us to generate Q and compensate. Generation or consumption of Q to make voltages in defined define limits called calls reactive power compensation. Reactive power compensation. That means that if you change the reactive power, even with capacitor or power plant, in aim of or in the purpose of making voltage in range, in a specified range, that's called as reactive power compensation. I think you know that the direct relation between voltage and reactive power. The voltage and reactive power act to each other directly, and active power and frequency relate directly. For example, if you want to improve your voltage in a bus, you can inject more Q on that bus. If you want to if you if you uh, if you see a frequency, your region frequency is increased, it means that your active power you of demand is decreases. The decreasing or demand results increasing in frequency. Another word, the increasing the demand, active power in demand, results decreasing frequency. Or for decrease the voltage level of a bus, you can inject, you can decrease the injection of reactive power. This is very important concept of the direct relation between voltage and reactive power. In other side, active power and frequency. After learning some notes about the general knowledge in load flow, we try to introduce two types of networks in this lesson. The networks type 1, we introduce a 5 buses networks with one generation in SLB bus, and other buses is PQ bus with a specified amount of loads. The bus number 2 or the type 2 uh, we locate another generation in bus number 4 and make this bus to PV bus. We try to solve power flow or load flow equation for these two types um, as a exercise. Okay, the networks type 1, as you see, we have ideal source in a slack bus, and the slack bus is termed as number 1. Other buses to uh, bus number 2 to bus number 5, all of them is PQ bus. And I'm so eager to discuss about these networks and parameters we introduce in these networks and preparing to solve power flow equation for this type. This table is talking about transmission line specification. For example, bus number 1 to bus number 2, number 1 to number 2. We have a transmission line and its series impedance is like this, ampere unit, and its admittance is J 0.02, and it seems that this transmission line is a average type. We have 3 types of a transmission line. The short one is a short transmission line. The average type or medium type is better than average. Medium type is modeled with series, and the parallel or shunt admittances is located to the end and the beginning of the transmission line. And the long type of transmission line has a complex model. But in this lesson or in this course, we only use medium type of transmission line. For example, when I want to model the transmission line between bus 1 and 2, we can write like this: Zij as a series impedance and the half part of admittances in the beginning and the half part of admittances in the end. The half part, the whole admittances is 0, 2, and the half part is J 0.01, and it is J 0.01 per unit, half amount of admittance in the end and in the beginning of transmission line. Cij onto, this is Ycij half. This is a model of medium type of transmission line. And when you want to write it on here, you can write it. Okay, this is J 0.01, and its impedance is 0.05 plus J 0.11. Another impedance and admittance of transmission line is described in table 2.2. This table only describes the specification of transmission line. This specification of transmission line is useful to determine Y bus. Do you know Y bus? Do you remember Y bus? We solve some example regarding Y bus in the first part of this chapter. Another table is about the amount of active power, reactive power in demand or generation. In this type of example, we have a power plant or generation in only a slack bus. And in a slack bus, generation in active and reactive power is unknown. Bus number 1, the type of bus is SLB or slack bus. Do we have any demand on this bus? No. Both of them is 0. Both of them are 0. And do we have any generation in bus number 1? Yes, but it's unknown. We write it majhul in Farsi. Majhul means unknown. Unknown means that you have to solve load flow to find P generation of bus 1, bus of a slack, and Q generation of a slack. And you have to find through load flow. Okay, the bus number 2 is PQ bus. PQ bus, also called as load bus. And the load in bus 2 is specified. For example, 40 megawatts plus J 20 megawatt. Only demand is determined, and other parameters like the amount of voltage or magnitude of voltage and its angle is unknown. For changing the megawatt to per unit, we have to divide the real part, for example megawatt or megavar, to its base. It is base. This base of power. And when you divide 40 megawatt on 100 megawatt, 100 megavolt volt ampere, is its result is 0.4 per unit, and you can see here or here. And since the bus number 2 is a PQ bus without any generation, the part of generation is 0. Other amount of demand in bus number 3, 4, and 5 is PQ bus, and its amount of active and reactive power can be determined as is written here, and the per unit amount of per unit can be calculated easily. Absolutely, the generation part is also 0 because of other other buses is PQ bus without any generation. This is a description of this table about the characteristic of active and reactive power generation and demand in each bus. Okay, another important information is finding pure injected power. Pi is pure injected active power, that is P generation in bus I minus P demand of I. In a slack bus, because the active and reactive power of generated power is unknown or it is unspecified, the injected power or a pure injected power is unknown or not specified. But in other buses, because of the PQ type of buses, we can write P number 2 injected, the pure injected power, active power in bus 2 is P generation of 2 minus P demand of 2. The generation is 0 and the calculation is minus 40 megawatts or minus 0.4 per unit. The all amount of PQ bus as pure injected active or reactive power is negative because of no generation and only demand makes this number negative. This example is very important as an final exam, and if you have any question you can ask me here or after watching the video which I will upload in YouTube. You can ask me your question in the next session. Okay, another sample of could you repeat again? Okay, another power system sample, or uh, we call it type 2. We locate an generation in bus number 4 and make this bus as a PV bus. The PV bus, the PV bus is a bus is a bus which a generation is located there. Okay, other part of networks is remain as before, and in bus number 4 the demand is 0, but the generation is here. In PV bus, 2 parameter is specified. Which parameter is specified? P and amount of voltage or magnitude of voltage. Which parameter is unknown? Q and the angle of voltage is not determined, and you can find them after load flow equation solving. For example, in this type of power system and PV bus, the demand is 0 in active and reactive power. P generation is determined or specified, and Q is not determined. Bus number 5 is PQ bus, as we see in before, and we have to make a table as specific the pure injection, injection in active power and reactive power. Only the bus number 4 is changed. The generation is 30 megawatt minus 0 as a load, and it would be positive 30 megawatt as a pure active power injection, and plus 0.3 per unit, and the pure injection of active power and reactive power is unknown. Other part of this table is like before, or the last table as you see in type 1, and everything is ready for starting calculation. Please pay attention more for starting the calculation. The first thing we have to calculate is why bus is used in load flow. We find load bus, Y bus in load flow before in the beginning of this chapter, and I want to remind you about the calculation of each array of this matrix. In diagonal part of matrix or arrays, which is yi and I in diagonal side, you have to inverse the z is located to sum of all impedances which connected to bus 1 bus number I, and Yij is minus sum of all impedances which connected to bus I and J. For example, Y31 is equal to Y13 is minus impedances. Impedances of impedances connected between bus number 1 and number 3 is number 1 as number 3. Number 1 and number 3 is here. This is impedance. I can impedance. No, I can correct. Please take a note to correct this. Admittances. This is impedances. Impedance between bus number 1 and number 3, as impedance is located between these two buses, 0.5 plus J 0.11 per unit, and you have to diverse this amount to finding admittances with a minus. Another array is y32 is equal to y23, 34, 45, and you have to calculate these parameters with your calculator. In a final exam, you have to bring your self calculator. Pay attention. Your self calculator is needed in final exam. Okay, I try to let me see about can we calculate here. Unfortunately not. Okay, please try and find this equation and these results in your home and with your calculator and find these numbers in your home. Okay, in type 2, in power system type 2, which is we continue. Okay, in type 2, the PV bus in bus number 4 is here, and the and in PV bus, we have two parameters of P generation, and the amount of voltage is determined or determined. Two parameters of Q generation and the angle of voltage is not specified, you unknown. In bus number 4 and the PV bus, the specified amount of voltage is set on 1 per unit. The Q generation of bus number 4 has a limitation, a maximum amount and minimum amount. This method calls the reactive power limitation or generate reactive power limitation. And the reactive power generation, the problem and this question give us as an input of this problem, and it is determined that the Q4 minimum, the minimum side of Q4 is minus 0.15 per unit, and the maximum is 0.2 per unit. Another information in bus number 1 and bus number 2, in voltage of slack bus is determined as 1 per unit with the degree of 0 degree. Okay, so we try to solve load flow equation with gauss cycle. In load flow equation, we introduced this matrix-based equation here, and we say that each row of the matrix can be extracted like this. For example, in the second array of pure injection خالص تزریقی pure injection is the extraction of y bus a multiple to the column of voltage, and you can write like this: P2 minus JQ2 on V2 conjugate is sigma Y2J multiple Vj. J is from bus number 1 to bus number n. For all buses can be write like this. And for example, in bus number 2, we can write like this: P2 minus JQ2 on V2 conjugate is Y21 V1 plus Y22 V2 plus Y23 V3 plus Y24 V4 plus Y25 V5. And when you want to finding, for example, V2 is here, we can write Y22 V2 is equal to P2 minus JQ2 on V2 conjugate minus Y21 V1 minus Y23 V3 minus Y24 V4 minus Y25 V5. And you can transfer Y22 in other side, Y22, and clear Y22 in the left side. And so we can write as a general formula to finding Vi V in bus I is 1 on YII multiple to a parenthesis, which is PI specified minus JQI specified over VI conjugate. We write this general equation on this exercise. We found this equation by trying, and I prefer to write general form for finding voltage on each buses here. Minus y I 1 V1 like this, minus sigma 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 J2 J2 under 5 Y I J V J. And you can see here like this. This part. I hear you, but I can't understand what you want. I is the number of your buses you want to calculate the voltage. For example, no. For example, I want to find voltage of bus number 2, and we change all of I here as 2, 2, or 2, and J is a counter, and you can count J from another part to the end. Okay. Another important thing we have to pay attention is uh, is we don't have the amount of VI. We write this formula to find VI, but in finding VI, we also use VI. It is not illegal. It is not uh, possible. The VI is unknown. But you, in finding VI procedure, you use VI again. It is possible? I answered this question with pre amount of VI. For finding voltage in Gauss-Seidel with iteration-based method. Like Gauss-Seidel, Newton-Raphson. These methods are based on a iteration. No, based on iteration. For example, when you want to get the final destination or final value, you have to try more and more, and each try gives you the better answer. For example, for finding vi, you have to try 10 iterations, and each iterations gives you the most accurate answer. Uh, the zero iteration called as first guess. The first guess, the first consumption. No, excuse me. The first guess is better word. The first guess is is about it's near the near place of your answer. I know that my answer to this equation is regarding or is about 19 to, for example, in per unit, between 0.9 to 1.2 per unit, and the best guess or the initial value to starting the iteration and finding the best answer is about 1 per unit. Here is about 1 per unit, amount of 9 and 1.2 per unit is a 1 per unit. The 1 per unit is the first guess or initial value or initial guess. Hope after writing this equation, we have to replace the first iteration with initial value. The initial value of all voltages is 1 per unit with the angle of 0. After finding the first iteration of each voltage, you have to substitute the new one with the old one. The first value is 1 per unit with 0 angle. It is the first one, or 0 iteration, 0 iteration, or initial value. This one iteration should be another number, another part. For example, 90 with minus 1 degree. You have to, in 2 iteration, you have to use the last update of iteration in the next iteration. For this reason, we extract this part from this part. This part is regarded the new part which has new amount of voltage we just calculate in the last iteration. But this part is not calculated yet, but you can replace with the old one. For this reason, we divide two parts with the new part and the old part. Again, in finding these two parts, some parts have a new update of amount of voltage we just calculated, and we calculated recently. Another part is not calculated yet. In the future we calculate these parts. So in this part we replace the amount of Vj with an update one. In this part we have to replace with the old one. This is why we replaced this expression. This expression is replaced with this expression, and we divide this expression with new one and the old one. Okay. Another point of this, in which criteria we can find that the iteration must be stopped. The convergence condition is when your the convergence conditions is when the new step of finding voltage minus the old step of that parameter is less than epsilon. Epsilon in this equation is about 10 in power of minus 4. With checking this equation, with checking this condition, you can stop the iteration and finalize the answers as a final answers. And after that, after finding Vj, you can calculate P1 and Q1. P1 as Q1 as the active power and reactive power of SLB. I think the other part of solving the problem or addressing the main equation in uh, power system type 1 would be done in next session, and I think it is I think we should finished here, and in the next session we continue. Thank you. If you have a question, I am here. I try to convert the video of this session and gives you YouTube links in the group. Thank you for coming in my class, and I hope you feel better in your academic time. Have a nice time. Have a nice time. Bye. Bye.